All right, so this is a continuation of the exam key. We're on number 12. Is the molecule livermorium oxide polar? And so the first thing to figure out is, do we have polar bonds? All polar molecules have polar bonds, remember, but not all polar bonds give rise to polar molecules. Okay, you can have non-polar bonds that have polar molecules in them if the dipole moments cancel out, right? And so first we have to figure out from our change in electronegativity between the two elements, do we have polar bonds? So we have livermorium oxygen bonds. Livermorium's down here on the periodic table. Oxygen is up here. And so you know right away that livermorium is going to be way less electronegative than oxygen due to our periodic trends. And oxygen has an electronegativity given to us of 3.5. And you look for going down, up, we're not given livermorium. But we are given tellurium. And so we know it's going to be equal to tellurium or less, right? So in the worst case scenario in terms of how polar this thing is going to be, it's going to be the same as tellurium, the tellurium oxygen bond. In reality, it's probably going to be electronegativity 2.0 or something like that, or 1.9. We don't know, it's not given to us, but let's see what happens if we plug in 2.1. We get 1.4, right? And so that is definitely a polar covalent. It's not a covalent. So we're going to have electron density pointed that way. And the structure of this molecule is correct. We can check it, how it's written. This is a bent molecule, right? Because we have a lone pair there. Steric number 3 with one lone pair gives us bent. So we're going to have a net dipole in this molecule pointing down. This is the same as the earlier example I gave in the key of sulfur dioxide, contrasting that with CO2, which was a linear molecule. And so, yes, it has polar bonds and is bent, therefore it is a polar molecule. Number 13. For the following, determine the difference in electronegativity and indicate whether the bond between the two atoms would be considered ionic, polar covalent, or covalent. So very similar to what we just did, right? And so, well, bromine and bromine, I could look it up. Okay, it's 2.8. I don't even have to. I know it's bromine and bromine. So it's the same thing minus the same thing. 2.8 minus 2.8 is 0. It's going to be covalent. So that cancels out B and cancels out C. Rubidium chloride, metal and a non-metal, probably going to be ionic. Let's check. Chlorine is 3. Rubidium is 0.8. 3 minus 0.8 is 2.2. That's greater than 2, so that's ionic. So unfortunately, both A and D are ionic, so it doesn't help me. SO, is it covalent or polar covalent? Turns out to be polar covalent. Why? Sulfur and oxygen, 3.5 minus 2.6 is 0.9, and that's in between 0.4 and 0.2. So the correct answer is D. It's a sulfur oxygen bond is polar covalent. All right, next one. This compound is used in fireworks, and when it's burned, it has a wavelength of 500 nanometers. What is the frequency and energy of this light? So we need to know our energy equations here. They're given to us on the formula sheet, but that's where we have to start out. And so we're given something in nanometers. We know that E equals H times nu, and lambda times nu equals C. Nu is, remember, the frequency. H is Planck's constant given to us. C is speed of light given to us. Lambda is the wavelength. That's all we have is wavelength. And first, well, we want frequency. So that's going to be lambda equals C divided by, nu equals C divided by lambda, dividing both sides by lambda. C is given to us as about 3 times 10 to the 8th meters per second, divided by 500 nanometers. 500 nanometers, we're going to have to convert into meters such that our units cancel. And so that's going to equal 5 times 10 to the minus 7th meters, nanometers on top and bottom. 5 times 10 to the minus 7 meters. That ends up getting you 6 times 10 to the 14th. And it's second inverse, which is the same as hertz, right? Those are two words for the same thing. So we know it's not B or C. And so at this point, we now have to use the other equation to help us out. And so the other equation, we want energy. Well, we have the frequency, and H is given to us. That's O is Planck's constant, 6.626 times 10 to the minus 34 joules seconds, times our frequency we just figured out, 10 to the 14th second inverse. And that, if you plug that into your calculator, is equal to about 4 times 10 to the minus 19 joules. And so that is A.